This is part 4 of a series on logistic regression. In this video, we will look at the multinomial or softmax regression for multiclass classification. This video was produced in Korean and translated into English. My voice was generated using AI text-to-speech. In the last video, we looked at the OVR method for multiclass classification. In this video, we will look at the multinomial logistic regression, or Softmax regression. Let's use the maximum likelihood estimation method to generate a loss function and use it to perform the multiclass classification. Let's take a look again at the data used in the previous video. The data has two features x1 and x2, and one target class y. The target y consists of 0, 1, and 2. One hot encode y for multiclass classification. This would then be encoded as follows. The first column is the probability that y is 0. The second column is the probability that y is 1, and the third column is the probability that y is 2. We split this data into 3 data sets as follows. Let's assume that the data sets are trained with 2 binary classification models, as shown below. Set the baseline or reference category. In the figure below, the probability that y is 0 is set as the baseline, and the second and third data sets are trained using a binary classification model, respectively. As you can see in the first video, we perform the linear regression using the log odds expression. Here, the denominator is the baseline probability. The denominator of the second model is also the baseline. This odds value is measured by how many times larger the probability is compared to the baseline. The log odds of the first data set would be something like this. This value is always 0. Therefore, we only need to consider 2 models. Let's say that when we feed a test data point into the models, the log odds of the first model is negative 1.0, and the log odds of the second model is positive 0.5. Since the positive 0.5 is the largest of the 3 log odds values, we predict the class of this test data point is 2. If the second model has a log odds value of negative 1.5, the log odds 0 is the largest, so the class of this test data point is predicted to be 0. And any class can be a baseline. While OVR actually requires training multiple binary classification models, this method estimates all parameters simultaneously using a single model. We'll look at this in detail later in the hands-on code. The probability that y is 0 can be written as follows. Therefore, this expression can be written like this. And this expression can also be written like this. By solving these 2 simultaneous equations, the probability that y is 1 and the probability that y is 2 can be written as follows, respectively. And the probability that y is 0 can be written like this. So in the end, it can be written like this. We can create the formulas to calculate each probability as follows. W1 and B1 are the parameters of the model 1, and W2 and B2 are the parameters of the model 2. If both W0 and B0 are set to 0, the constant 1 can be expressed as follows. Then the equation on the left can be written like this. Simplifying this equation, the probability that y is 1 will be like this. This is the softmax function, where C is the number of classes. All remaining probabilities can also be expressed as softmax like this. In binary classification, a logistic function is used to calculate these probabilities. Softmax regression for multiclass classification uses the softmax function instead of the logistic function. This time, we will look at the loss function for softmax regression. Binary classification uses a binary cross-entropy loss function, generated by the logistic function and the maximum likelihood estimation method. Similar to binary classification, we can use MLE to generate a loss function for softmax regression. This loss function is cross-entropy. This is a general expression for binary cross-entropy. And the regularization can also be applied to cross-entropy as well. The softmax function created on the previous page is as follows. In binary classification, the probability of y is expressed as follows. Please refer to this video for this expression. Using the indicator function, it can be expressed as follows. The classes are 0 and 1. The probability that the class is 1 is y hat, and the probability that the class is 0 is 1 minus y hat. Even for multiclass classification, this probability can be written as follows. The number of classes is C. The indicator function is defined like this. For mathematical convenience, we use the log likelihood function. This equation can be written as below. And the original y values are 1 hot encoded as follows. Let's denote the first column like this and the second and third columns like this, respectively. We know that this value is 1 only if y is equal to k. If y and k are different, it is 0. Therefore, the indicator function can be expressed like this. Then this equation can be written as follows. This is the negative cross-entropy. If we sum up all the negative cross-entropy over all the data points, this is the negative loss function for softmax regression. Our goal is to maximize this negative loss function. Let's see why. Suppose the 1 hot encoded y values are predicted as follows. For the first data point, the probability that the class is 0 is 0.1, the probability that it is 1 is 0.7, and the probability that it is 2 is 0.2. Since the probability that the class is 1 is highest, this is a good prediction. The second data point is predicted to be 0, since the probability that the class is 0 is highest, so it is a wrong prediction. The third data point is predicted to be 0, since the probability that the class is 0 is highest, so it's a good prediction. Now let's calculate this probability. The calculation results are like this. You can see that the probability values for correctly predicted data points are large. The probability values for incorrectly predicted data points are small like this. The larger this probability value, the better the prediction. Maximizing this value will improve the performance of this model. Therefore, we can create the objective function as follows. The goal is to find W and B that maximize the negative loss function J. By changing the sign of J, we can change this part to minimize it. Then this part becomes cross-entropy. Therefore, the final objective function can be written as follows. In summary, the objective function for multi-class classification is to minimize the cross-entropy. Here y hat is softmax. In comparison, binary classification uses a logistic function to minimize the binary cross-entropy. And in multiclass classification as well, the regularization term can be added as follows. Now, let's implement Softmax regression using SciPy's optimized library. Let's train and make predictions on the iris dataset using Softmax and the cross-entropy. We will use the SciPy instead of the scikit-learn to better understand how it works. Read the iris dataset. Convert y to one-hot encoding. Then split the feature X and one-hot encoded Y into the training and test data. As in binary classification, we add a column vector of all ones to the feature X matrix. Set the regularization constant to 0.01. Let's write a function to calculate softmax as follows. And write a function to calculate the loss function as follows. Since the parameter w is input as a one-dimensional vector, it is converted to a two-dimensional structure. The structure of the W matrix is as follows. The number of rows is the number of classes, and the number of columns is the number of parameters W. Since iris data has 4 features, there are 4 W's and 1 intercept B. Next, we calculate the loss value for the training data. Calculate the dot product of W and train X and convert it to softmax. This is the y hat. The structure of the y hat is like this. The number of rows is the number of training data points, and the number of columns is the number of classes. The first column is the probability that y is 0. The second and third columns are also the probabilities that y is 1 and 2. Then we use the y hat to calculate the cross-entropy. Add the ridge regularization term here. Next, we calculate the loss value for the test data in the same way above. This has nothing to do with the training process and is only meant to observe changes in loss later. Save the train loss and test loss. Now we perform the optimization process. All parameters W are initialized to point 1. The parameter W is a matrix with 3 rows and 5 columns like this. The number of rows is the number of classes. The first column is the intercept B, and the remaining columns are the slope W. We use this as a one-dimensional structure. We used these conditions previously when creating the softmax function. These are the constraints of this optimization problem. Let's use the first row as the baseline category. This part corresponds to B0 and the remaining part corresponds to W0. Therefore, we can fix the first row to all zeros. These constraints can be expressed like this. This means that each W of n is all 0. Next, we use SciPy's optimize.minimize function to minimize the loss function defined above. The initial values of the parameters are passed as a one-dimensional structure. Constraints are the conditions set above. And the training and test data are passed as arguments. After the optimization process is finished, check the results. The result.x variable contains the estimated parameters. Next, we measure the accuracy of the test data. Convert the estimated parameters into a two-dimensional structure. The structure is like this. Finding the dot product of the parameters and the test data points and taking the softmax gives the estimated probability. The structure of the y-prob is like this. The class with the highest probability value becomes the estimated class y-pred. The y-pred of the first test data point will be 2. This is because 0.7 is the highest. And we use the actual and estimated y values to measure the accuracy. Next, visually check the train loss and test loss measured during the training process. And check the estimated parameters. Let's check the results. The optimization process has converged successfully. The estimated parameters are as follows. A total of 15 parameters are estimated. If this vector is converted to a two-dimensional structure, it becomes a matrix with 3 rows and 5 columns. The accuracy of the test data are measured at 100%. The estimated W matrix is as follows. The first row is all 0 because it is the baseline or reference category. And the history of the train loss and test loss are like this. We can see that both decrease significantly as the iteration progresses. Let's run this code. The results came out like this. Let's check the predicted probabilities, y-prob, for the classes of the test data. The probabilities for each class are as follows. For the first test data point, the class y is predicted to be 0 because the probability that y is 0 is highest. Lastly, let's implement Softmax Regression using scikit-learn's logistic regression library. Let's train and make predictions on the iris dataset using the multiclass argument in the logistic regression as multinomial. Read the iris dataset and split it into the training and test data. Create a logistic regression model. Set the multiclass argument to multinomial. Then we fit this model to the training data. Next, we predict the classes of the test data. We then use actual and predicted y values to measure the accuracy. And let's check the estimated parameters. The accuracy of the test data is measured at 0.974. The 12 parameters W are estimated as follows. And the 3 intercepts B are estimated like this. A total of 15 parameters are estimated. Here, these parameters are all non-zero values. We cannot find any baseline category. I haven't yet figured out how scikit-learn handles the baseline or reference category. Let's run this code. The results came out like this. So far, we have looked at multinomial or softmax logistic regression, In the next video, we will look at locally weighted logistic regression.